So that covers all the operations of A-B trees. But actually the toughest part of analyzing these A-B trees is actually coming up with the analysis for the cost of the operations. First thing we can observe is that if B is exactly 2A minus 1, then it's not a good case because every update could cause rebalancing. And this is an example that is shown here. So we have the following tree where essentially this tree is completely full, right? So every, so in this case, A is 2, so that means B is 3. So this is a 2, 3, 3. The leaves have exactly 3 elements, so they're full, and every internal node at this point has exactly 3 children, so therefore they're also full. Once you do an insert, then you'll see that this leaf will overflow, so it needs to be split in 2, which means that its parents need to be split in 2, and so on. Okay? So therefore you could really cause all the way rebalancing. But of course, if you then delete the element you just inserted, you go back to this situation. Okay, so by inserting and deleting the same element, we could essentially waste a lot of time. This is not, it's still within log, all of the other operations can be done log and time, but it's not good. The interesting thing is that if B is 2 times A, then the updates cause constant number of rebalancing operations. If B is greater than 2 times A, then the number of rebalancing operations is actually this value. Okay. And if we could somehow set B to be, say, 3 times A, then this ends up being some 1 over A factor, which means that most operations do not actually cause rebalancing. We're going to in fact look at a special case or easy case where B equals 4 times A, and then we're going to show that updates can actually cause 1 over A log base A of n operations, rebalancing operations. So therefore the total number of rebalancing operations is going to be very small. This is going to be very useful in the IO model because in fact every node will represent an IO. So therefore we want to have as few rebalancing operations as possible to reduce the IO cost of insertion and deletion into these trees. Yeah. So what can we say about this case? Okay. So after we do a split, you can see that a leaf contains roughly 4 times A, because that's the value of B, divided by 2 plus minus 1 elements. So that's going to be roughly 2A elements. Okay. So therefore we could allow it to have a potential of A elements. If a leaf node has 2A elements, then we can do at least A deletions and at least 2 times A insertions before we need to do some operation. We need to do split or fusing operation into that. Similarly, if you do a fuse operation because of maybe a deletion, then you'll see that the leaf will have between this much and this much elements. And of course, if it has 5 times A, we have to do something. But if it has 5 times A, then we split it, right? So we'll have 2.5 and 2.5. So the whole point is that both split and fuse will end up in a situation where you have a node that has a number of elements that is quite far from the bound, from the extreme. It is roughly plus minus A, or a constant factor times A, away from the boundary case. So therefore we could allow it a charge of A over 2 insertion or deletions before we have to do something. And that's basically ends up being a very easy charging argument. Every time we do a split or fuse, we give the node A over 2 charges, or if you want to do the amortized analysis, money or coin, and every insertion or deletion uses 1 coin. And then you could see that with that operation, the expected the amortized cost of rebalancing or insertion, would be 1 over 8 times log base A of n, because every rebalancing or every split and fuse will require theta A insertion or deletion update in general. Okay. And then by setting A and B to be theta of B, we can get that we have a data structure that has n over B space, has the optimal query time, and also has optimal update time. Okay. And this is sometimes called a B plus tree, because in this data structure we have assumed that the elements only appear in the leaves, and the internal nodes are just keys that guide the search.